Hi everyone. Today we're continuing Chapter 6. Last time we talked about the states of matter, solids, liquids, and gases, and today we're going to focus on gases. So first we're going to talk about what are called gas laws, and gas laws are mathematical equations that describe the behavior of gases as they are mixed, subjected to pressure or temperature changes, or allowed to diffuse. So down below is a table that summarizes all of the different gas laws that we can use to determine, for instance, let's say we change the pressure of a gas. How will that affect its volume or its temperature? So we can use these different laws to predict what will happen. And these laws were derived many, many years ago from different experiments that scientists conducted. And so you'll notice that some of these laws are named after specific scientists. So Boyle has a law, Charles has a law, Dalton has a law, Graham has a law. And these experiments that they conducted were actually pretty simple experiments, but they were able to prove relationships between pressure and temperature, pressure and volume, temperature and volume, etc. So there are a few symbols we're going to use for these gas laws. So P is pressure, V is volume, T is temperature, and then later on we'll use N for moles or amount. All right, so let's look at the first law. But before we do that, we do want to kind of go over pressure and temperature a little bit because that will help us better understand these laws. So let's start with temperature. Or pressure, excuse me. So pressure is defined as a force per unit area of surface on which the force acts. And in gas law calculations, pressure is often expressed in units related to the measurement of atmospheric pressure. So off on the right-hand side, we have something called a Mercury Barometer. And how this works is we have mercury at the bottom here, so it's a little mercury pool. And then the atmosphere exerts a pressure on that mercury. And the pressure of the atmosphere can change depending on a few different factors. So for instance, if it's kind of a rainy day, maybe a little colder out, the pressure of the atmosphere is a little bit less than normal. But if it's a nice hot day, then the pressure of the atmosphere is a little bit higher than normal. Now, what ends up happening due to this atmospheric pressure is mercury will rise up this column, and the height of the mercury in that column depends on the pressure of the atmosphere. Now, typically, if we're at sea level, which here in Tacoma we are, the pressure of the atmosphere is what we call 1 atmosphere. So P equals 1 atmosphere. Now that corresponds to a height of 760 millimeters of mercury. So we can say that 1 atmosphere of pressure will result in a mercury height of 760 millimeters. Now, sometimes this is measured in centimeters or inches, But in science, we often use millimeters of mercury as kind of our standard. All right. So again, the standard atmosphere of pressure is the pressure needed to support a 760 millimeter column of mercury in a barometer. And that's equivalent to 76 centimeters. So sometimes we'll use different units depending on the situation. And then 1 torr of pressure, so this is another type of unit for pressure. This is the pressure needed to support a 1 millimeter column of mercury in a barometer. So a pressure of 760 torr is equal to 1 standard atmosphere. So this is just another unit that we can use. We said that 1 atmosphere is equal to 760 millimeters of mercury, but 1 atmosphere is also equal to 760 torr. So what that tells us is 1 millimeter of mercury is equal to 1 torr. So there are a lot of different units of pressure, which can get a little confusing. Torr is actually a unit that was named after Evangelista Torricelli, who was a physicist in Italy. And again, it's equivalent to millimeters of mercury. There's also pounds per square inch, which you might be more familiar with if you've ever filled up your tires on a bike or a car. And then there's also bar, there's all sorts of units. Now, most often in chemistry, we're going to use atmospheres or millimeters of mercury. And your textbook does have a table that summarizes different units of pressure. So again, we're typically going to use millimeters of mercury and atmospheres. But remember, if you do see the unit torr, that is equal to millimeters of mercury. So those are interchangeable. And then here in America, we tend to use pounds per square inch. So 1 atmosphere of pressure is equal to 14.7 pounds per square inch, or PSI. There's also the unit of bar. So 1 atmosphere is equal to 1.01 bar. So they're essentially equivalent. And then there's also kilopascals. So for every 1 atmosphere of pressure, there's 101 kilopascals of pressure. And then off to the right, you can see some typical applications for each unit. So for compressed gases, we typically use PSI, and in meteorology, we typically use bar. All right, now the other thing we need to talk a little bit more about is temperature. We did talk about temperature a few chapters ago, but just to review, the temperature of a gas sample is a measurement of the average kinetic energy of the gas molecules in the sample. So what we can say there is that kinetic energy is proportional to temperature. So the more energetic a gas is, the higher its temperature. And then the less energetic the gas is, the lower the temperature. So kinetic energy and temperature are directly related to each other. Now, for gas laws, we're always going to use the Kelvin temperature scale. So you might remember back when we first talked about temperature, that the Kelvin scale, which is off to the right, that is an all positive scale. So we don't have any negative temperatures. And that's going to be very important for our gas laws, because sometimes we're going to see that a particular variable is in the denominator of a fraction. And if you have a negative value, that could lead to negative values of pressure or negative values of volume, and that's not possible, right? So we want to make sure that all of our temperature values are positive. So we're going to use the Kelvin scale. Now, in the Kelvin scale, the lowest possible temperature is 0 Kelvin, and that's also called absolute zero. And this is the temperature at which gas molecules have no kinetic energy because all motion stops. Now, if we were to relate that to the Celsius scale, that would equal negative 273 degrees Celsius. And then in Fahrenheit, that would correspond to negative 459 degrees Fahrenheit. Now remember, if we want to convert Celsius to Kelvin, that equals the temperature in Celsius plus 273. And that's just due to that difference between absolute zero values. Or you could also kind of look up here at the freezing point of water as well. Okay. So let's start with our first gas law, Boyle's law. So this is a gas law that describes the pressure and volume behavior of a gas sample that is maintained at constant temperature. So the temperature of the system is not changing, and we can also assume that the amount of the gas is not changing. So in these equations, P is the pressure, V is the volume, and K is an experimentally determined constant. So down below, we can see that pressure is inversely related to volume. Now, what we can do is move volume over to the left-hand side, and then we get the relationship where pressure times volume equals a constant. So what's great about that is we can write out a law allowing us to take into account any changes. So that law is P1 V1 equals P2 V2. So the P1 and V1 refer to an initial pressure and an initial volume. And then P2 and V2 refer to a final pressure and a final volume. So for instance, if we look at the figure on the right, we have a gas in a cylinder with a movable piston on the top. So if we pull that piston up, we're increasing the volume, and that's going to decrease the pressure of the gas. So the gas will have more room to move around, so it's not going to collide with any surfaces as often. And typically when we're building up pressure, it's because a gas is hitting things really rapidly and energetically. So if there's more room for a gas to kind of spread out, then that's going to decrease the pressure of the overall gas. However, if we push down on the piston and we decrease the volume, that's going to increase the pressure of the gas. So the gas is kind of pushing back on the piston with more force, and it's colliding more often with that piston and also the walls around it. So those gas molecules are going to be more energetic and build up more pressure. So let's look at an example where we can use Boyle's law. So let's say that we have a gas in a cylinder with a movable piston, just like in our previous diagram. Initially, the volume of the gas is 50 milliliters and the pressure is 755 millimeters of mercury. If the volume changes to 100 milliliters, what is the new pressure of the gas? Assume the amount of the gas N and the temperature T are constant. So down below, imagine we have a gas in that cylinder, and initially the volume of the gas is 50 milliliters, and the initial pressure is 755 millimeters of mercury. So that's our V1 and P1. And then we're going to double the volume to 100 milliliters. And we want to figure out what is the new pressure or the final pressure. So if pressure and volume are inversely related to each other, what's going to happen to the pressure when we increase the volume? So will the pressure increase or decrease? So on the last slide, we said that if volume increases, pressure will decrease. So here we're going to expect a smaller pressure because we're expecting the pressure to decrease after we increase the volume. Okay, so let's do this calculation. So again, we're going to use that equation P1 V1 equals P2 V2. And there's a couple different ways that you can set this up. So you could just directly plug in your values that you know, and then solve for the value that you don't know. Or you could rearrange the equation initially to solve for the variable that we don't know. So if we do that, we're trying to isolate P2 and solve for that. So that will equal P1 times V1 over V2. So we're just dividing both sides by V2 and we'll get that resulting equation. Okay, so now we're just going to plug in what we know. So P1 was 755 millimeters of mercury. V1 is 50 milliliters. And V2 is 100 milliliters. Okay, so let's cancel units. So milliliters will cancel with milliliters, and we'll be left with millimeters of mercury. Okay, so we're going to plug into our calculators 755 times 50 over 100. Now, how many significant figures should we have in our final answer? So here we have all multiplication and division. So remember, we only care about the least amount of sig figs. And 755 has 3 sig figs, 50.0 has 3 sig figs, and 100.0 has 4 sig figs. So we want our answer to have 3 sig figs. Remember, we want to reflect our least accurate values. So your calculator is going to give you 377.5 millimeters of mercury, but we want to round that to 3 sig figs. So we would round that to 378 millimeters of mercury. And that answer makes sense. It's smaller than our original pressure, which we expected. So that works out. Okay, The next law is Charles's law. So this is a gas law that describes the temperature and volume behavior of a gas that is maintained at constant pressure. We can also assume that the amount of the gas is constant as well. So in these equations, V is the volume, T is the temperature, in Kelvin, that's very important. And then K prime is an experimentally determined constant. So volume is directly proportional to temperature. So we can see that down below in this equation. So if we move temperature over to the left-hand side, we can see that V over T, or volume over temperature, is equal to a constant. So we could write an expression where an initial volume over an initial temperature will equal a final volume over a final temperature. And both of those expressions, V1 over T1 and V2 over T2, will both equal that constant K prime. So that's why we can set those equal to each other. So let's say in this figure here on the right, we have a gas in a cylinder with a movable piston again. And we have a particular initial volume and initial temperature. Now, if we increase the temperature of the gas, remember that kinetic energy is proportional to temperature. So as we're increasing the temperature, we're also increasing the energy of the gas. So the gas is going to start pushing and bouncing off of the walls and the piston with more force and more energy. And that's actually going to cause the piston to rise up. And that's going to increase the volume. Now again, here we're assuming the pressure is staying constant. So the only real thing that can change here is the volume, because that's going to accommodate the pressure. So we're going to keep the pressure constant by raising that piston. Okay, so let's look at an example problem. So again, we have a gas in a cylinder with a movable piston. And initially, the volume of the gas, V1, is 50 milliliters. And then the temperature, T1, is 25 degrees Celsius. If the temperature increases to T2, 35 degrees Celsius, what is the new volume of the gas? And again, we're going to assume that the amount of the gas N and the pressure P are constant. So remember, we need these values for temperature to be in Kelvin. So we're going to add 273 to each of those values in degrees Celsius. So the initial temperature in Kelvin will be 298, and then the final temperature in Kelvin will be 308. So those are the temperature values that we'll use in our equation. Okay, so let's set up our equation. So we're trying to solve for V2. So I'm going to multiply both sides by T2, and that will give us that V2 is equal to V1 over T1 times T2. So now we can plug in our values. So 50 milliliters is our initial volume. T2 is 308 Kelvin, and T1 is 298 Kelvin. Okay, so looking at those numbers, how many sig figs should we have in our final answer? So our temperature values are in Kelvin, and when they're in Kelvin, there's 3 sig figs. And then our volume also has 3 sig figs. So our final answer should also have 3 sig figs. So when we plug this into our calculator, we should find a volume of 51.7 milliliters. So remember to cancel our units. So we have Kelvin in the numerator and the denominator. So we'll be left with units of volume. Okay, so not too bad. Once you know the gas law, plugging in values is pretty standard. Now let's talk about the combined gas law. So this law combines Boyle's law and Charles's law. So what this tells us is that pressure times volume over temperature is equal to a constant. So we could set that equal. So we could say this is our initial pressure, initial volume, initial temperature. And that same constant is also equal to the ratio of the final pressure, the final volume, over the final temperature. So down below, you can see that the combined gas law tells us that the initial pressure times the initial volume over the initial temperature is equal to the final pressure times the final volume over the final temperature. So this is great because all that's held constant here is the amount of the gas. So in these experiments, we're allowing for a change in pressure, a change in temperature, and a change in volume. So let's go over an example. A gas sample has a volume, so we'll say V1, of 2.5 liters when it is at a temperature, T1, of 30 degrees Celsius. And remember, we want that to be in Kelvin, so we're going to add 273. And then we have an initial pressure of 1.8 atmospheres. So what volume in liters, so V2 is unknown, will the sample have if the pressure is increased, so P2 is equal to 3 atmospheres, and the temperature is increased, T2 is equal to 100 degrees Celsius. And remember again, we want to use Kelvin, so we'll add 273 to our temperature. Okay, so let's figure out what our temperatures are in Kelvin. So 30 plus 273, that will be 303 Kelvin. And then 100 plus 273 is 373 Kelvin. All right, so now all that's left is we just have to plug everything into the combined gas law. So remember, P1 times V1 over T1 is equal to P2 times V2. Oh, I'll leave out the X there. I don't want to confuse you. P2 times V2 over T2. All right, so we're trying to solve for V2. So let's multiply both sides by T2 over P2, because that will cancel out the right-hand side pressure and temperature, and then it will move everything over to the left-hand side. So then V2 is equal to P1 times V1 times T2 over P2 times T1. That's a lot. Okay, so let's plug in all of our values. So we said P1 is 1.8 atmospheres. V1 was 2.5 liters. And then T2 in Kelvin was 373. All right, and then we're going to divide that by P2, which we said was 3 atmospheres, and T1, which we said was 303 Kelvin. Okay, so let's cancel some units here. So we have atmospheres in the numerator and denominator. We also, oh, sorry, I'm giving away the answer there. We also have Kelvin over Kelvin, and we're left with liters, which is perfect because we're trying to find our new volume in liters. All right, so let's plug this into our calculator. So we're going to multiply 1.8 by 2.5 by 373. And then we're going to divide that by 3 times 303. Okay, so what we should end up with is 1.85 liters. Okay. So our volume actually decreased from our initial volume. All right, so there's also some solution slides here. So you probably already saw I accidentally clicked ahead. So again, this problem that we were given was solved using the combined gas law. And let's say we didn't know which law to use. We did have volume, pressure, and temperature given to us in this problem. And the only law that we have that uses all 3 variables is the combined gas law. So that's how we would know to use that particular law. And then we also identified the initial and final conditions. We also made sure that all quantities that are alike were in the same units. So all the temperature quantities were in Kelvin. All of the pressure quantities were in atmospheres. And of course, we expressed temperature in Kelvin. And if you like to make a table, you can, and this will kind of help you organize all of the values that you're given. And then we plugged everything into the combined gas law, and we found that the final volume was 1.85 liters. So I think we'll stop there today. Next time we'll go over a couple more gas laws. So we'll talk about Avogadro's law as well as the ideal gas law. And the ideal gas law and Avogadro's law both incorporate the amount of a gas. So what happens when the amount of a gas changes? So we'll find out next time.